Great. Okay, so I hope you all had a pleasant study break, a productive or a relaxing one, or perhaps even both. We're going to pick up with the last few slides from last week, and we're going to just finish off from last lecture, what we spoke about with the probabilistic distributions, and then we're going to move on to the last part of this section. And then, so we'll get to that in 10, 15 minutes or so. I don't know how long it's going to take. So you'll remember that last time we finished up by talking about the central limit theorem and basically why Gaussians are super common to find in the natural sciences. And what we're going to be, and we ended up by sort of coming up with a means of showing that if you had arbitrarily distributed data and you took averages of subsets of those data, you would get something that looks like a Gaussian. Now, we finished the lecture last week, and I want to, because we buzzed through it, and I want to go through it a little bit more. By defining the student t distribution, the student t distribution looks a lot like the M statistic that we had from this statistic here that we had on the last slide from the central limit theorem, with one important difference. The main important difference is this little guy down here is a sigma, and that is the standard deviation of the population. And when we're doing an analysis, we don't necessarily know that. That's usually one of the things that we're trying to find. Instead, what we frequently have is the standard deviation of the sample that we're analyzing. And so if you reformulate this in terms of the sample standard deviation, then what you end up with is this thing called the t statistic. And the t statistic is then useful for the t distribution, the student t distribution. Don't worry, I'm not going to expect you to remember any of that actual formula. Which the main utility of it is that it has sort of the exact behavior that we would expect of observed data in the central limit theorem. That is to say that when you have many, many, many observations, so you're averaging together hundreds of objects at a time, you end up with something that looks very, very Gaussian. So the Gaussian here is shown by the dotted lines, and you can't even see the dotted line behind the dashed line there, because they're essentially exactly the same. And the dashed line there is the student t distribution. So in the limit of many, many observations, the student t and the Gaussian distributions look the same. Whereas that's not true as you go to fewer observations. So if you're averaging together, 3 observations at a time, then you end up with something that has very, very complex and wide wings. And those wings are real. Those come from the fact that the wings of the central limit theorem are the slowest to converge. And you end up with this more Lorentzian, Cauchy sort of looking distribution. But it's one that is still modeled very well by the student t distribution. So that's just where we ended up last week, or last lecture rather. The second last distribution that we're going to talk about is an important one. It's called the chi-squared distribution. It's the Greek letter chi. And it's also related to the central limit theorem. And so the way in which you construct the chi-squared distribution is that you sum squared deviations of the observations. So this is your chi-squared statistic. And so it is the squared deviation from mean divided by the population standard deviation. And you can then use the chi-squared statistic to define the chi-squared distribution. And that's this thing that you can see here. Again, don't worry about remembering it. The functional form of it, but you should remember the details of it. And one of the reasons that chi-squared and the chi-squared statistic is so common and so popular is because of the use that it has in model fitting. So in terms of finding goodness of fit and finding how well a model fits a particular distribution. And so the way in which that's usually used in data is by looking at what's called the reduced chi-squared. And the reduced chi-squared is just the chi-squared, or is frequently formulated as the chi-squared divided by nu, where nu here, the Greek letter nu, is the degrees of freedom of the distribution. The reason that this is used is because in the limit of very, very large n, the chi-squared distribution divided by the expectation rather of the chi-squared distribution divided by the degrees of freedom is 1. That is the average of the chi-squared distribution divided by the degrees of freedom is 1. However, one thing that is often overlooked in a lot of literature, and is something that I think it's useful for you to know from the outset, is that a lot of model optimization does what's called maximum likelihood optimization. That is, it doesn't find the average of a distribution, it finds the maximum of a distribution. And the maximum, or the mode, is different for the chi-squared distribution than the mean. And what that means is that if you're actually optimizing to the mode of this distribution, the chi-squared distribution that you've the mode that you've optimized to is not equal to the expectation. And so it's not the same as chi-squared divided by nu. Rather, it's actually chi-squared divided by nu minus 2. And so whenever you see in the literature somebody that says we perform a maximum likelihood fit and we calculate the reduced chi-squared of chi-squared divided by nu, that's wrong. Okay, so the maximum likelihood is best calculated, or should be correctly calculated, using this particular formulation for what's called the reduced chi-squared divided by nu minus 2. Chi-squared distribution has the expectation nu, as I just said, so that's the average, and variance of 2 nu. So it's a pretty simple distribution, but very, very powerful, and something that we're going to use a bit later in the course as well in our model fitting. So we'll get to that. There's now 2 little questions that I want to talk about, that I want to ask you, sort of polls that I want to make about the distributions that we've looked at, and what you think, what your instinct is about a couple of things. So the first thing I want to talk to you, I want you to answer is, I'm going to hide the results, is this particular scenario. So we have a wealth simulation, and we consider 1,000 people. Each of those 1,000 people has $1,000, and we take 2 of those people at random, and we undergo some sort of a transaction. That is, that we take a fixed portion of one person's income and we give it to another. Okay, and we then repeat that process 100,000 times. What does the final distribution of wealth look like? What do you think the final distribution of wealth in this scheme is? Now, the people are chosen totally at random. There's no systematic bias in who gets selected. And the fraction of their income is also chosen totally at random. So it's a purely random process. Okay? So I'll give you a second to answer that question. Okay, so we've got sort of 4 responses there. Let's see how many people are online. We've got 13 people online, so I'll wait till we get sort of little over 2/3 of the number of responses. Okay. So that's the first scenario. The second scenario is another poll that I'm about to put up. So if you do want to answer this one, you need to do it right now. The second scenario is this one here. Is for totally legitimate, non-illegal reasons, you need to fabricate a series of transactions to pad out a table of real transactions so that your fabricated numbers are indistinguishable from real transactions. Okay, so you need to come up with or fill in a whole bunch of transactions on a table so that they look like real ones. Now, the transactions can range from being very, very small, a few cents, all the way up to very, very large, many thousands of dollars. But crucially, the table is listed in scientific notation. Okay, so this is what you're seeing. This is your table. Okay, and you need to basically fill in values from that table. My question to you is, in order to do this well, so that it's indistinguishable from real transactions, you want your fake numbers to look as much like random numbers from this list as all of the others. What will the histogram of the numbers, the digits in front of the decimal point look like if you do your job well and they all look totally random, like they're real responses, real transactions. So that is to say, if I take this table and I throw away everything from the decimal point onwards, and I just calculate the histogram of the numbers at the front, what does that distribution look like? Okay, so that's the next poll. So it's the histogram of first digits, hiding the results again. So what does the distribution look like? Does it look like a uniform distribution from 1 to 9? Does it look like a Gaussian centered on 5, or does it look like a skewed distribution, preferencing one side or the other? Okay, so that's the second poll that we want, and we have 8, 9, nearly 10 responses. Once we have 10, okay, so let's go back now to our wealth and equality. So we have 10 responses from both. Great. Okay, so the final distribution that we're going to talk about is what's called the Pareto distribution, or the power law distribution, or rather truncated power law. The Pareto distribution has this form, so it's a probability distribution, right? So it's sampleable, and it has this form: alpha x to the alpha divided by x to the alpha plus 1, and is defined over a domain of x is greater than some minimum value xm, and it's 0 otherwise. Okay. It's named after this dude, Vilfredo Pareto, who used it very famously in a measure or a demonstration of wealth disparity, which probably gives you an indication of where this is going. So if I show the results here, people seem to think that that distribution is overwhelmingly going to produce a Gaussian, when in reality, if you do that exact simulation, what you end up with is a distribution that looks like this. So the input data, everybody started with $1,000. And as you do that series of random transactions, wealth asymmetrically piles up on a couple of individuals, and the overwhelming majority of people end up broke. And the reason this is such a famous distribution, the Pareto distribution is named after this person who showed this for the first time, is because it has a lot of applications in economics and a whole bunch of other things. And it led to a very famous law in economics called the 80-20 law, which basically says that 80% of a company's profit comes from 20% of the people. And that's essentially these 20%, the people who have all of the wealth, right? And so what happens is, this is also a really nice demonstration of just why, having a totally fair society with no governmental intervention and no governmental sort of regulation of who gets what in terms of benefit is flawed. Because basically, if you just say, I'm just going to let things be totally fair, totally random, then what happens is, you end up with these huge wealth disparities. These power law functions are actually really common in the natural sciences, particularly in some branches. And the reason is because they represent relationships between any two variables where a proportional change in one variable has a proportional change on another variable. Okay, so it's all to do with relative change in proportion. Okay, so examples that you're probably all familiar with, or some of you will be familiar with, Kepler's third law of planetary motion. The stellar initial mass function is a power law. In physics, the Stefan-Boltzmann law is a power law, and every single inverse square law, as the name suggests, is a power law, right? So these are all of your electrostatics, all of your gravitation equations, right? There's also one other interesting, I find very interesting application of the power law, which is called Benford's law. And Benford's law relates to our second poll. So our second poll said, what happens if we have a histogram of a table which spans many orders of magnitude in terms of the numbers, and we just calculate the histogram of the first digit of those numbers, the first significant digit, right? Because obviously you could pad it with as many zeros as you want. The first significant digit. What is the histogram of that distribution? Now, the majority of you have said uniform, totally understandably, right? The intuitive reaction to that, I would argue, but many of you clearly have also, figured out where I was going, is that this should be some sort of a uniform distribution. But in fact, it's not. If you actually calculate what's called the first digit law, the Benford's law, the leading digit of a listing of numbers that spans multiple orders of magnitude, many, many decades in value, is preferentially 1. And then it's 2, and then next least likely is 3, next least likely is 4, and it's a power law. It follows this particular distribution, this logarithmic distribution here, and this is the distribution. So this red line here is Benford's law, and the blue histogram here is a simulation where I have just done exactly this experiment. I've created a 10,000 observations of data that spanned from 10 to the minus 3 to 10 to the 3 in value. I've then truncated these values to only the first digit. You don't need to understand what these two lines are doing, just so that you know. I've truncated these values to be just the first digit, and then I've done a histogram of those first digits. And that's the blue histogram you can see here. And it perfectly matches Benford's law. Right? The reason this is quite interesting, or the reason I find this quite amusing, is because this is a counterintuitive result. And it's a counterintuitive result that means that people who don't know about Benford's law, who are trying to commit the sort of fraud that we were just discussing of padding out tables, will often fall problem of, because they will say, oh, there's already a lot of 1s in this table, I'll throw in a few 5s and 7s and 9s. But that then biases the distribution away from Benford's law and is a sign of fraud, right? And so this is actually one of the ways in which people find tax fraud. Fun fact. Don't use your powers for evil. So the Pareto distribution has these properties. It has an expectation that's undefined for alpha of less, or rather is infinite for alpha of less than or equal to 1, because it diverges. And then for alpha is greater than 1, the expectation is this form here, alpha x to the m divided by alpha minus 1. And similarly, the variance is undefined if it's if the value of alpha is between 1 and 2, inclusive of 1. And those brackets are backwards. No, they're not. No, that's right. So inclusive of 2, not inclusive of 1. And yes, and you end up with this variance here. Great. Okay, cool. So that's the end of this. That's the last of the probability distributions that we were going to discuss, which is good because now we can move right along to our next series, next lecture. I'm going to show the Q&A just in case there's any questions, and I'll turn off the poll. Excellent. Okay, so the last lecture, the last chapter in this particular section of the lecture course is on random numbers, simulation, and sampling. Okay, now I asked you at the beginning. Oh, I wanted to turn that actually. I need to make sure that this poll is still on. Okay, so I asked at the beginning if people had any if people had any opinions as to what the distribution of these data should look like. So we have a coin toss rather, and we have it's a fair coin, and it should therefore we've already seen what distribution that has in earlier lectures, and we want to know what properties should the distribution have and what properties should the individual observations have. So we've only got one response there so far. So if people want to, I mean, don't feel pressured, obviously, but if people want to put in responses, then please do. The reason that we're asking this question is because this is all to do, generating simulated data is essentially what this whole section is all about, this chapter. So in the empirical sciences, as I said earlier, we're frequently interested in generating samples of data from various distributions. Be that for something which we call Monte Carlo simulations, which we're going to talk about a bit later, or for looking at actual values and models and expectations and things like that. whatever the application that we're looking at, the goal of this process is to generate a series of data that are statistically indistinguishable from the underlying model that we want to be generating, or we want these distributions to follow, right? That leads to two questions. The first of which is, how do we do it? How do we actually generate fake data? And how do we generate it in a way that is indistinguishable from a true process in nature that generates a distribution of data that we want to model? The second of which is, how can it be done efficiently, well? And so to some extent, we don't really care about the first point, about the second point, because just doing it is enough, right? But actually generating efficient sampling can actually tell us interesting stuff about how we run this and how we do this sort of sampling. So this whole section is going to be on sampling and simulation. So we go back to this question of generating data. Congrats to the one person who managed to oh, two people. Oh, go team. Okay, come on. We're in a battle now. All right. So our word cloud has officially 2 responses, which means that there can be more than one size if people said the same thing more than once. So what are the properties of the distribution? What are the properties of the individual data that are important? Okay, great. So the binomial distribution, number of observations, obviously important. They have the same probability, obviously important. Excellent, excellent, excellent. Discrete. So it's, yeah, the uniform distribution is the correct one. Sorry, the binomial distribution is the correct one. The uniform distribution is for values that can land between 0 and 1, right? Whereas with the coin toss, we have only 0 or 1 because of the head or tail. So my responses here were, it's bimodal with only 2 possible values, which already gets us to 1, 2, 3 of the responses. So it follows the binomial distribution. There's equal chance of both outcomes, same probabilities, great job. And they're independent observations. Okay, so the independence of the observations is an important one, because if we're generating simulated data, we want those observations to be indistinguishable from random draws of the underlying distribution. And if there's correlation between the draws that we make, then by definition, they're not random, right? So it's important to have the observations be independent. That leads us to an important question, which is, how do you generate random numbers? And this is by far and away not a simple thing to do, and it's quite a complicated field of study. Truly random numbers follow absolutely no predictable sequence, and they have no periodicity. They have no repetition over any period of time. You can watch them till the end of the universe, and they will never show any sort of periodicity. They'll never show any sort of correlation or predictability in their sequence. True random numbers, generally speaking, can only be generated from actual, real, true random processes in nature. There is no mechanism that we can use to generate truly random numbers that doesn't involve some sort of true random process that we can observe and monitor. So good examples of those of truly random processes are like thermal noise, so heat, and quantum mechanical processes are obviously very, very good examples of random processes, because by definition they're not predictable. Okay, in nowadays, I mean, initially, and going back many decades, generating random numbers, truly random numbers, is an extremely difficult task, extremely difficult, extremely hard to do. However, nowadays it's less of a barrier, because nowadays there are dedicated teams, dedicated tools that we have out of the box that you can just take and use that will give you truly random numbers. And a good example of that is one of these there's a package in R called QRandom, and that generates truly random numbers. And the way in which it generates truly random numbers is by looking at by querying a database, or rather an experiment that is ongoing at a university in Canberra in Australia called the Australian National University, ANU. And that experiment has a device that monitors the electromagnetic field of a vacuum. Now, in quantum mechanics and quantum physics, the vacuum is not an empty space. It contains a 0-point energy that's constantly causing virtual particles to be populated, and those virtual particles carry with them some sort of electromagnetic field, right? And therefore, they create the electromagnetic field of the vacuum chamber shows fluctuations, random fluctuations, because of the, popping into and out of existence of all of these vacuum virtual particles. And therefore, if you look at the electromagnetic field of a vacuum and you monitor it, the fluctuations that you see represent random numbers, represent random fluctuations that you can convert into truly random numbers. And so you can use this function QRandom to just generate truly random numbers. And I compiled this lecture, 3 minutes before the start of the lecture in Markdown. And these 5 numbers are real random numbers that were observed from that experiment right now, or, then. And so if I was to run this again, the exact same thing, then I would get a totally different set of numbers. And there is no way that I could predict the numbers that are going to come out. Their website's actually quite neat, mostly because they have a bunch of little tools and things in there. Just give me 1 second. I will show you. There we go. So, right, so this is the website from ANU. And one of the neat things about the website is that it has a bunch of tools that you can use to actually visualize the random numbers, right? So here's an example. This is just a totally white noise random image generated by the random fluctuations that they're observing right now in this experiment. They also have a bunch of live streams, random colors. They also have a bunch of ways of visualizing these things. So this is a great example of randomness. So this is generating using the random numbers that they are measuring right now in the experiment. They generate a sequence of colors, and this color sequence is truly random. There is no periodicity to it. There is no predictability to it. Okay. And so this is just one of the neat little things. But we do this in terms of the numbers rather than the actual, we don't necessarily want to look at colors, and apologize to anyone who has photosensitivity, because that might have looked a bit weird. Okay. However, that's really neat and that's really useful and really interesting, but querying an internet link to Australia for your project might seem like overkill, especially because making that query takes time, right? It takes time for the experiment to observe n numbers, and those n numbers then have to be sent to you over the internet, and then you would use them in your experiment. But it takes a finite period of time for you to generate for them to observe the numbers that you've queried, essentially. In practice, therefore, we've basically never actually used true random numbers in our day-to-day science. Instead, what we do is we settle for a sequence of numbers that looks very much like truly random numbers, but which isn't. Okay? And so that is what we call the pseudo-random numbers. Okay? Computers, as they currently exist, I mean, quantum computers will probably change this, but computers as they currently exist are deterministic machines. That is, that when you give them a particular input, they will give you a particular output, and only one particular output, right? There is no mechanism for them to generate a probabilistic outcome given a finite input, okay? But given that we want random numbers, we can't satisfy with having, we can't be satisfied with having just deterministic numbers. We need to have something that is random, that is indistinguishable from true random, at least over some finite interval. And so that's where pseudo-random numbers comes in, because what they do is they use deterministic machines, deterministic sequences of numbers that appear to be random over a finite sequence. They have some periodicity, they have some variant, there's some repetition over time, but in discrete chunks, they appear random, truly random. Okay, for all mathematical intents and purposes. Pseudo-random numbers, like I said, they're generated over a finite sequence, but they are still deterministic. They display randomness over a finite sequence, but they are still deterministic. So the way in which we can demonstrate that is because in practice, in order to create these sequences of random numbers, we have to specify a starting point because the machine is deterministic. And that starting point is what we refer to as the random seed. So what I can do is I can set a random seed to be 666, totally random number. And I can then generate 5 random numbers on the interval 1 to 256. Okay, and I do that and I get these 5 numbers here, 190, 98, 51, 250, 52, 93, right? I then generate another 5 random numbers and I get 5 different numbers, 190, 250, 128, 4, and 67. If I now reset the seed back to 666, then what I do is I reinitialize the sequence that the computer is using to generate its deterministic random numbers. And that means that if I run my random 5, if I run this line again, what will I get out? I'll get out the same 5 numbers that I got out initially. Because the machine isn't generating truly random numbers, it's generating pseudo-random numbers based off some seed. And I've just reseeded the entire process. And so the whole process, the chain of random numbers, starts afresh from the same point. And because it's deterministic, it goes to 198, and then again to 51, then again to 250, et cetera, et cetera, et cetera. Nowadays, there are algorithms that generate pseudo-random numbers that are extremely complex. Okay, that generate very, very high quality pseudo-random numbers, and we're going to talk about them in a second, but there are also ones that are very, very simple at heart. And one of them is called the linear congruential generator. And we're going to show you, we're going to create our own random number generator right now. Okay, so the linear congruential, not a good word, generator basically proceeds like this. It has 3 integers, m, a, and b, okay, which specify, m specifies the range of numbers that are going to come out, and a and b specify how the algorithm basically creates its chain. It's also got a random seed, which we call x0, and x0 obviously has to sit within 0 to m minus 1. So the way in which we use the linear congruential generator to generate random numbers is by a recurrence. And so by using this recursion relation, and the recursion relation starts with x equals 0, which is the seed that we specify, and then it generates the next value in the random sequence, xk plus 1, as being a times k plus b, all modulus by m. Okay, so this modulus m is the thing that gives you the finite range of the numbers, and it's also a crucial part in making the numbers appear random. So x mod y, as I said, refers to the modulus of x and y. So the remainder, for those of you who don't remember what that term means. It's the remainder that you get when you divide x by y. this is a pretty simple function, right? This is just a single recursion relation. So it's pretty easy for us to actually write up, for us to code up. So we can do that pretty easily, just in a few lines. And then we can pick a couple of numbers. So we can pick values for A, we can pick values for B. And let's say that we're going to set M to be 2 to the power of 16. So we want to generate what's called 16-bit numbers. And so our random numbers are going to vary from 0 to 2 to the power of 16 minus 1. Let's choose again a random seed, which again I've chosen as 666 for no particular reason. And I'm now going to actually run this algorithm just by randomly assigning A and B. Okay, so I've just got a different random number generator. I know this is technically cheating, but I got a different random number generator, and I said, give me, pseudo-random numbers of A and B over this range. And I've then plotted the results of our random number generator on 0 to 2 to the power of 16 minus 1. Okay, now if this is truly random, it should look something like a uniform distribution with some random structure in it. And what you can see is that first thing to notice is that every A value here is odd. Okay, the reason that every A value here is odd is because if A is even, this whole algorithm breaks. Okay, because you end up just getting a single value out, right? So that I've excluded from the possibilities just because there's no point. It just distracts. So we've taken all of these A values have to be odd. And I've then plotted the distribution of these uniform variables. And there's a couple of things that you can notice. Firstly, you notice that they all look different. So the choice of A and B is having a significant impact on the quality of the random numbers that we get out. The second thing is that there are quite clearly some combinations of A and B, like the ones that just went past, which are very bad because they end up giving you periodic structures in your random numbers, right? And those are bad. Those are not what we want. We don't want anything with any sort of periodicity. We want something that appears to be truly random. So as I said, some of these lead to catastrophic failures where you get these, big gaps and periodic jumps like the one that just flashed by. But if we choose them wisely, if we choose the values of A and B carefully, then you can actually end up getting something that looks pretty good, right? So here I've just chosen 2 prime numbers, turns out to look pretty good, 7 and 13. It's not the optimum. I want to make that abundantly clear. There are much better choices of these 2 things that are well studied in the literature, in the mathematics literature, but it's not really relevant to what we're going to talk about here, so I'm not going to go into it. But this looks pretty good. This looks pretty reasonable. Internally in R, you don't have to do this yourself, right? As I said, because these random number generators are so heavily used in statistics and in all natural sciences that having good random number generators is basically a given in any modern statistical programming language. So you can get them in R and Python. They're available within base R and within NumPy. In R, the base pseudo-random number generator is called the Mersenne-Twister generator. And the details of that, I'm not going to go into. It's considerably more complicated than what we've just generated. But we can compare the Mersenne-Twister generator to our method, our simple linear congruency method, using our prime numbers, so up here. And what we end up seeing is this. So here I've given the MT uniform random distribution is shown as the hashed red lines, and the blue is our version. And the first thing you might think when you look at that is that, well, actually the blue one looks more random. More random in inverted commas. It looks like it's more uniform. So we've generated 10 to the 4 observations here, 10 to the 4 samples from both of the random generators, and we've plotted the histogram of them. The question is, how much structure do we expect to see if we actually generated random numbers? If we had truly random numbers and 10 to the 4 observations, how much random structure do you actually expect there to be? And we can do that. We can actually check because we have this tool which generates true random numbers from A and U. And so we can just take the vacuum numbers that come out of A and U and we can plot them over the MT algorithm. And what we end up with is this. So the true random numbers are now shown in the back in blue, and the MT random numbers are now shown in red. And these are much closer. So it turns out that our linear congruency random number generator was actually generating numbers that were too evenly distributed to be random, which is not necessarily intuitive, right? But you can think about it as having, if you instead of generating random numbers, you generated a perfect sequence, 1, 2, 3, 4, 5, 6, 7, 8, all the way along this histogram, right? Then, and the number of observations that you had was exactly 2 to the 16, that histogram would look perfectly flat. But those are not random numbers. And so there is structure in randomness. And so these random number generators have to create the right amount of curious structure in the randomness. And so it's a complex thing. One of the things that also isn't shown by these histograms is the periodicity. So is that when I generate my string of random numbers, do I generate them in such a way that there's 10 things that look random, but then it loops and the sequence is like a sawtooth, for example? That would be not random, right? Because the numbers would go up and then they would drop and then they would go up and the values might change, but there's some underlying periodicity, some underlying trend in the numbers, right? And one of the things that you don't see by this is that the linear congruency generator that we created has a maximum period of M. So if you pick those A and B values to be the best possible values, the maximum period that you can have is M, which is 2 to the 16, which is not basically good enough for the vast majority of applications. However, the Mersenne-Twister algorithm has a period of 2 to the power of 19,937 minus 1, which is functionally infinite for basically all applications, which means that the pseudo-random numbers that we get out of the Mersenne-Twister algorithm is basically functionally truly random, except for the fact that it requires a seed. And so it is still deterministic. And that means that if you run this algorithm with the same seed, you always get the same pseudo-random numbers. It's an important thing to remember. Okay, so that's good. That's all well and good about random numbers. But what about random variables? Well, I mean, these are kind of what we're interested in. We don't really care about whether or not I can generate a list of numbers from 1 to 256 that is random. Because, I mean, okay, great. What am I going to do with that? What we're really interested in is being able to use sequences of random numbers to generate random variables, to generate observations from a particular distribution that is statistically indistinguishable from true random draws from that distribution. And what I'm sure many of you are actually realizing or thinking now is that we've actually been doing this a lot already. I mean, we did it earlier today in the last lecture when we used the uniform random function in R to generate a set of uniform random data points, right? The question is, how do we do it? Or how are we doing it? Generally, when we do this, when we generate random uniform variables, what we're interested in doing is learning something about the distribution underlying those random variables. And you might be thinking that this sounds a bit tautological. It sounds like a bit of a circular loop, right? We're trying to use some distribution to define random numbers so that we can learn something about the distribution. Totally understandable. It'll become clear in a couple of slides why this is very, very powerful. So bear with me. What we want to do is we want to generate realizations of observations of variables that look like they were drawn from this truly random process that has some probability density function that we're interested in, that we want to probe. And this, before we begin, we need to understand the concept of independent and identically distributed data. Truly random observations from a PDF, from a particular distribution function, density function, are what are called independent and identically distributed. So you'll remember when we were talking about the coin toss, we said that one of the fundamental things that our realizations need to be is they need to be independent. And that's one of the fundamental tenets of having random draws from a distribution, is that the draws are independent of one another. The second important thing, which is almost tautological, is that they be identically distributed. That is, that they all come from the same underlying PDF, the same underlying probability function that we're interested in. And so these are what we call IID observations, identically distributed or independent and identically distributed observations. You're going to see this term a lot over the course of the next probably 4 lectures and your academic careers, I imagine. But particularly when we're discussing simulation, which we're going to be doing a lot today. There's also another reason that we might want to generate fake data, and that's for something that's called Monte Carlo integration. So if you've heard that term before, then great. If you haven't, don't worry. We're going to be talking about it in a few slides' time. So what exactly is simulation? What do we mean when we say simulation? Well, like we said in the last slide, it's trying to generate, using a deterministic sequence, apparently random draws from some underlying distribution. So a deterministic sequence of numbers that are for all statistically appropriate tests are indistinguishable from truly random observations from that distribution. So using this phrase we just learned, we want to generate IID observations from some target distribution. There's many ways to generate these sorts of IID observations, provided that we have access to pseudo-random numbers or truly random numbers. And as we've seen already with our little generator, we can do that. We do have access to those even on a deterministic machine. So this is something that we can do. So this is now asking the question, how do we do it? Why do we do it? What do we do? The first way in which you can generate IID observations from a particular distribution, from an analytic, usually a standard statistical distribution, is by direct sampling. And that is to say that somebody's done it for you. There are ways to generate from an analytic distribution of data and create random IID observations from that distribution. And it's true for lots of statistical distributions. Almost every statistical distribution that you could possibly think of. Certainly all of the ones we've learned about already here. So I'm going to give you a few examples. So here, let's go back to our coin tossing example where now we've got a biased coin. So the probability of throwing a head is only 30%. And there's only one possible success. So, size is equal to 1 is the number of possible ways to succeed. And this is using the R function random binomial. And this is the format that basically all statistical random direct samplings have in R. They follow this R and then the name of the function. The number of observations we want, the size, and then the properties that determine the probabilistic distribution that we're interested in, that we're analyzing. So here I'm generating 10,000 observations from the binomial, and I just printed 3 of them just for fun, and you can see that they're 1, 0, 0. And you can do exactly the same thing in Python using NumPy. So NumPy has this thing random, this submodule random, and in random there is all of these a significant number of statistical distributions that you can sample from. Very similar syntax, just that the size is at the other end in Python, and so you end up with this. I've done 4,000 observations here. So 4,000 observations of a random binomial with the same probability and size from over here. I'm just accessing the values from the R session. That's what that little R dot means. And I printed out 3 of them just for funsies. And you can see that this time, because of our biased coin, we didn't throw a single head. We only threw 3 tails. And if I plot the distribution, oh, that's a typo. If I plot the distribution of the binomial function that comes out of this R rand and pi rand, then the distributions are in red and blue, and you can see that they're basically identical. And that they follow the expectation, that is that the PDF is bimodal, it's got 2 discrete values, and it preferentially selects things at 0 because it's a biased coin. Hopefully that's clear. We can play the exact same game for bunches of other distributions. So here we have, I'm going to expand this just for a minute. So here we have the uniform distribution where we've done exactly the same game. I've specified the limits of my uniform distribution to be 10 to 50. I've then generated 1,000 observations of that and 4,000 observations over here. And we end up with this probability distribution here, where you can see I've got the analytic distribution as the black dashed line and the distribution from R and Python as the blue and red respectively. Again, same thing with the Gaussian distribution using R norm now in Python, in R, and random normal in R. Again, for the Gaussian distribution, we have to specify the mean and the standard deviation. And you end up with, again, similar behavior. And the last, oh no, there's 2 more. The second last one I'm going to show you is the beta distribution. Again, R beta. The beta distribution, you'll remember, is governed by 2 shape variables, shape 1 and shape 2. And here I've chosen those to be 10 and 50 again. And again, we get exactly the same behavior between R and Python using random beta in Python. And the last one is the gamma distribution, which is an unbound distribution. So it goes off to infinity if you really let it. And here it's governed by a single shape factor. And I've just created random gamma for 1,000 draws and random gamma for 4,000 draws. And you end up with the 2 PDFs that you can see here. There are many, 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 many more that are available in both R and Python. So like I said, almost any statistical distribution that you could possibly think of already has random draws available for you to use within R and Python for your science. And we'll see why those are going to be useful in a slide's time or 2. What happens if we have a distribution where we can't directly sample from it? Let's say that it's a complex univariate distribution that doesn't have a well-defined, sampling distribution. It's not just a Gaussian or something. In that circumstance, we can generate a perfect sampling from an arbitrary univariate distribution, so a distribution that only varies in one variable, using what's called inversion sampling. Inversion sampling is extremely powerful for generating random draws from a univariate distribution, provided we're able to generate random draws on a uniform distribution, which we are, because we've already seen. We made our own random sampler. We've demonstrated that R has the random uniform. We just saw it on the last slide. And therefore, if we can generate pseudo-random numbers on the uniform 0, 1, that means that we can draw random IID observations from any almost univariate distribution, okay? Using the inversion sampling method. How does it work? Okay, so the way in which it works is we start with our IID random variable U, and which is drawn from the uniform random density, which is just 0 to 1. It has a value of 1 if it's between 0 and 1. It's 0 otherwise. No surprise. Okay, and we have some target function f that we want to draw IID observations from. The distribution of true IID observations of f are x, so those are the variables. But if these x are IID observations of f, of the distribution f, then that means that if I sub in the values of x into my function f, the distribution of these values is the uniform distribution, 0 to 1. This here, this is known as the probability integral transform, or PIT. Okay, so let me explain why that is for a second, because I know that's probably counterintuitive. And I think we have a little bit of time. Okay, so let's say that I have a Gaussian distribution, okay, and my Gaussian distribution is the sample in which I'm drawing things from. So this is my x, and this is my f of x. This is the probability distribution function for this particular distribution. If I draw random variables, right, that look something like that, what the PIT is essentially saying is that the probability that I draw a value that is x1, or rather is x is less than or equal to x1. So the probability of this thing here is related exclusively to the amount of probability density in that tail. So that is to say, how often do I expect to see a value that is less than or equal to x1? I expect to see it that many % of the time. Taking this to its logical limits, if x1 is out here, then that probability is 0. Okay, so the PIT so the probability of me observing a variable that is less than or equal to x is minus infinity is 0. The probability of me seeing a variable that is less than or equal to positive infinity is 1. And these are random draws, right? So the probability of observing this thing here, the probability of observing any value less than or equal to some value xi is directly related to the amount of probability mass that the distribution has below that value, right? And so that means that if I look at the distribution of this value, right, for each of these observations. So here, this one at the first data point, the value of f of x at that point is going to give me, I don't know, some value, 20%, right? And if I do this for all of these different distributions, the number of times that I see something that is at 100% is very, very small, because it's in the tail of this distribution here. The number of times that I see something that is at 0% is very, very small. Rather, the number of times I see things that are out here in the tail where there is 0 probability is very, very small. But if I equally sample over this entire X space, so if I then if I take equal spaced observations, right, then I would end up with a distribution that, looks like this Gaussian, basically, right? So if I actually played this game for equal draws of X, for uniform draws in X, okay, then what I would end up with is I'd take a value here, and f of x would be, 0. And I would take a value here, and it would be 0. I would take a value here, it would be 0. And so I'd get lots and lots of zeros, right? If I then take values here, here, and here, then they have values 50%, 51%, 52%, right? And so I get basically a function that decreases like this until I get to the middle, and then it will increase again as I get to the tail, because I'm taking uniform, not random, uniform draws of the value x. I'm asking, what is the value of f of x at every value x, right? But the crucial point is this. If you have random draws, you are more likely to see observations around the peak of the distribution. right? So this effect is counteracted by the fact that you end up observing the mean more often than anything else. And then you observe near the mean more often. And then you observe this a little bit and this a little bit, right? And what ends up happening is that these two things balance each other and you end up getting a uniform distribution. Okay, so that's where the PIT comes from. Don't worry if my hand drawing wasn't very good, because we're going to see this in action in a second. For those of you who are mathematically inclined, the way in which you can think about this is that you're essentially taking a function f and you're calculating the inverse of the cumulative distribution function. Okay, so if we have uniform random variables, so IID observations from this uniform distribution, then the distribution of values of the inverse of f evaluated at all of our uniform draws actually it produces the probability distribution f. And I know that sounds complicated and probably like it doesn't make any sense. So let's just see it in action, because it's a lot easier to understand when you just watch it happen in real time. So let's do this. Let's create some complicated function, which is a piecewise function that's made up of all these different random bits and bobs. Okay, and let's plot it. So this is our piecewise function. This is how I've coded it up, just as a function, and I then plot it. And this is my piecewise function. It's a bit of a roller coaster. It's got a whole bunch of random bumps and discontinuities and this and that. Difficult to sample from analytically. Okay. I then want to generate IID observations from this distribution using inversion sampling. So what I do is I take this distribution and I calculate the cumulative distribution function. So, I start down here and I say the sum, so this becomes the CDF, which is just then the cumulative distribution function we're all familiar with from earlier on. And the CDF looks like this. I'm trying not to have spoilers here. So this is the CDF of that distribution we have up there. What I then do is I invert the CDF, that is to say I'm now just basically flipping the axes because I'm looking over here. And I want to calculate the value of uniform random 0, 1 observations on that inverse of the CDF. So for every uniform random value, I trace to here, and then I drop it down onto the x-axis. And that gives me my value x, my sample from the distribution I'm interested in. Yeah. And this kind of is a visual you can kind of get an idea of visually why this works. Because if you take a uniform random value that's near 0, the probability that you sit right down here is very small, right? And so you're essentially passing all of these observations, these uniform random draws, through a filter that is the inverse of the cumulative distribution function, and that produces samples from the distribution we're interested in. And so now I'm running this sampling for a few thousand times, and you can see it building up as I perform uniform random draws of 0, 1, and then pass them through the cumulative distribution function, or the inverse of the cumulative distribution function. I find this particular animation is very, very helpful to understand what inverse sampling is doing. Hopefully you think the same, but if not, please feel free to let me know. So if the function is univariate and invertible, inversion sampling is an extremely powerful way of generating simulated variables, IID observations, from a particular distribution that is arbitrarily complex, provided it is invertible. Right? That was my caveat from earlier. Another point is that it's 0 loss. At no point here have any of my randomly generated variables been discarded. They all end up in the probability distribution. for this variable x, which is not what we can say for other forms of sampling, which we're going to talk about next. So the next thing we're going to talk about is what's called rejection sampling. If we have a distribution that isn't invertible or isn't univariate, so has more than one dimension, you can't use inversion sampling. Okay, so in that regime, what we need to do is we need to come up with a different mechanism to generate samples from this possibly bivariate, possibly multivariate distribution using our initial 0, 1 observations. Okay, and so the way in which we're going to do this is using what's called rejection sampling. And so the basis of rejection sampling, the idea behind it, is that you simulate 0, 1 on your uniform distribution, but then you only accept those observations as coming from the distribution that you're interested in if they satisfy some probability P. Okay, and that P, which you decide, if you define it correctly, will then lead you to having a distribution that follows the underlying PDF of the target distribution that you're interested in. So we can do this. Let's imagine that the piecewise function we just defined on our last slide, let's imagine for a second that it wasn't invertible. It is, but forget about it. Let's just pretend it's not. Okay. And we're going to use rejection sampling to generate independent observations from this particular distribution. Okay. So the way we're going to do this is we're going to define a rectangle, a box. Okay. And our rectangle is this black dashed line. And we're going to generate uniform random variables within that black box. And I'm then going to say, if the value of x and y falls beneath the curve that we're interested in, the target distribution, keep that observation. Otherwise, throw it away, reject it. Hence the name rejection sample. What does this look like in practice? Well, what we do is we simulate, we simulate some observation from, that should actually be uniform 0, 1. Yeah. So we simulate from uniform 0, 1, x value, rather from x1 to x0 to x min to x max, not 0, 1 necessarily. We then simulate the same uniform distribution y on y min to y max, which here is defined as 0 to 2.5. And we then keep the observation if the value y is less than the target distribution evaluated at the value x. Okay, what does that look like if we actually do it? It looks like this. So here we've generated 10,000 observations in our rectangle, and we've evaluated that inequality at every single pair of points, x, y. And if the x value was accepted, it ends up in red. And if it was rejected, it ends up in black. The underlying distribution is in blue in the background. And the PDF of the samples that are accepted is shown in purple. And you can see it traces the underlying distribution, which really nicely, which is as you would hope. And so this is one mechanism that we have for performing sampling. But this mechanism for sampling, its efficiency depends on how many samples we're throwing away. So you can imagine if I extended the rectangle up to 5 instead of 2, we'd be throwing away the vast majority of the data, the samples. Even here, we're throwing away quite a lot of the data, quite a lot of the random uniform samples. And therefore, it's quite expensive if the distributions don't match one another, if the underlying PDF is not rectangular. And so what we can do is we can come up with a slightly better formulation of this rejection sampling that has a slightly higher efficiency that helps us. And that's what's called adaptive rejection sampling. And this is where my typo G came from. I copy pasted, so apologies for that. The way in which our adaptive rejection sampling works is that instead of having a rectangle and generating samples from that rectangle on uniform 0, uniform Y1 y0, y1, and uniform x0, x1, what we have is a different distribution, some distribution that we can sample from and sample from easily. So any of those standard statistical distributions that we spoke about earlier, okay? And we call that distribution g of x. And that functional form can be, like I said, can be anything that we can sample from. And the reason that, and we pick that function such that the true target distribution is less than or equal to k times g of x, where k is just some arbitrary constant, for all values of x. Let's see what I mean in a second. So let's again demonstrate this with our piecewise function. So we have our piecewise function. We know that our piecewise function was skewed to the right, and it has a truncation. It has finite endpoints, which makes it perfect for the beta function. Beta function is defined over a finite range, and it's flexible enough to be able to be skewed in one direction or the other. So we're going to use a beta function as our g of x. Okay, and if I plot the beta function for our g of x, I get this black dotted line here. Okay, so essentially you can see already what I'm doing. We're just generating a function that is a tighter fit to the target distribution than the rectangle that we were using originally. It's essentially all we're doing, okay? And because we reject fewer samples, the actual quality of the PDF improves for the same number of random realizations, because the number of random realizations is not the same as the number of accepted samples. Right? So we're generating 10 to the 4 random realizations, but a good fraction of those get thrown out. So how good your acceptance is will directly relate to how high quality, how high fidelity the final PDF is. So the reason, why does this whole thing work, or how does this actually proceed? So this is the condition that I said before. So we have to select a distribution g of x such that the value of f of x, our target distribution, is less than k times g of x for all values of x. K here I've specified as 1.2 in order to just get the peak up above there and get that line above that little edge there. And this k is just a value that you select. You select it so that the distribution encompasses the target at all values. If we then define some acceptance rate, okay, the acceptance rate, h, as a function of x, is just the ratio between the target distribution and the sample distribution, right, multiplied by this k factor. So in cases where there is no density in the target distribution, obviously there is no acceptance. In cases where the target distribution and the generating distribution are very, very similar, the acceptance rate is nearly 100%. Okay, that's what hx is. It's this acceptance rate, the ratio between these two lines. We then know that the intersection of the probability or the cumulative distribution of x being less than some values, this is the cumulative distribution function, and x being accepted is just the integration from -infinity to x of our CDF times the acceptance rate. Okay, this is what I was trying to draw very, very poorly over here, this integral, right? The probability that anything gets accepted is obviously just the integral over this whole thing from -infinity to infinity, right? And that gives you, from the definition of conditional probability, this formula here. So we've already spoken about conditional probability before in previous weeks. And if you combine these two things, then what you end up finding is that the conditional probability of x being less than or equal to some value x, and given that it was accepted, is equal to the integral from -infinity to x of f of y dy, divided by the integral from -infinity to infinity of f of y dy. F of y is a random arbitrary function with no normalization. And so this normalization here turns f of y into a PDF. And that is to say that the probability distribution of acceptance of rather x being less than some value x, given that it was accepted, has the PDF of f. And that's why it works. Okay. One other thing to note is that this integral here, this probability of being accepted, is the integral from minus infinity to infinity of the distribution function times the acceptance rate, and that drops out to end up from the definition of the acceptance rate, drops out to just being 1 over k. So the probability of accepting something is directly related to your k value. The efficiency of this algorithm is directly related to how much you have to ratchet the amplitude of your target, of your sampling distribution up. And so that's an important thing to recognize. Oh, my slide change is busted. I'll fix that. The last thing that we're going to speak about is a very widely used application of random number generation, which is called Monte Carlo integration. And so Monte Carlo integration is essentially a form of random number sampling in order to estimate the value of an integral. And it's related quite heavily to rejection sampling in a way that we'll see in a second. So let's take a really simple example. Let's try and estimate the value of pi. Okay. The way we're going to do that is we're going to start with a unit square or a unit sphere. Well, sorry, it's not a unit square, rather. I've ratcheted it up a little bit. It'll be a unit square in a few minutes time. And I'm going to generate random IID observations, uniform observations on x and y, both with this distribution function. Okay. And so if I do that, what I end up getting is some set of pairs, some set of observations, xi, yi, and they reside within the domain minus 1.5 to 1.5 in both x and y. I can then ask the question, how many of these observations reside within the unit circle by just calculating x squared plus y squared is less than or equal to 1. And we can take the ratio of the number of samples that satisfy this criterion, this unit circle criterion, to the total number of random samples. And that gives us an estimate of pi. Actually, this is missing a prefactor that we'll see in a second. So I can do this. I can actually do this. I can simulate this. I can generate random observations, and I can calculate the value of pi. And what you can see is that when I start out with an estimate of 3.2, which is good enough for most astronomers, certainly not for particle physicists. And as we increase the number of observations, the noise on that particular estimate of pi goes down, and you end up converging towards the true value of pi in the limit of infinite numbers of random samples. So the accuracy of the estimate is related to the number of accepted samples, again, just like in rejection sampling. So we can shrink down the volume to actually be the unit square, and then we get many, many more accepted values, and we end up getting a much better estimate of pi. Right? Makes sense. Looking at why this works sort of in a more rigorous sense, it essentially involves this, like I said before in words, this approximation of a multi-dimensional integral by generating from non-deterministic random number, pseudo-random numbers, an estimate of the integral. And this is different to doing something which is fully deterministic, like using the trapezoidal rule to estimate the area under a curve, right? And part of the reason this is really useful is for when there is either a very highly multi-dimensional problem or the distribution function is very, very complicated. You can basically generate an estimate of the multi-dimensional integral I by integrating over some parameter space, omega, given this distribution function, given this acceptance function f of x dx. So the volume, this is the prefactor term that I said was missing above because I wasn't integrating over a unit square, which I should have been doing, which was naughty of me. The volume prefactor is the integral of the entire parameter space. Okay. And so that we're interested in. And so for our, we'll look at this in a sec. And so the Monte Carlo simulation, the approximation of the integral I is just equal to the volume divided by the number of samples times the acceptance rate, times the acceptance function, the number of samples that are accepted by our distribution. And this thing, 1 over n, says the sum of f of x, is just the expectation of f of x, right? So that is to say that the approximation to this integral is the volume that we're probing times the expectation of the success function. And that's actually quite a powerful tool. That's quite a powerful result, one that you can have a play with in your own time. So in the case of our estimate of pi, what did we have? We had some distribution that was f, and our success function in this case, our distribution is this. We have a value that is 1 if the variable falls between 0 and it has a value of x1 squared plus x2 squared is less than or equal to 1, and it's 0 otherwise. So that is this, the red circle, the red points are 1 and the blue points are 0. Okay. And so the volume of our parameter space in our minus 1.5 to 1.5 case is 9, right? Because we go from 1.5 is, so that's 3 units on a side. And so you end up with a volume of 9. And so the estimate of our integral is 9 over the number of samples times the sum of the acceptance function. So basically the number of accepted samples, this thing can be, you can think of that as this thing is here. And so we can actually, we did this, we can use our Monte Carlo simulation to estimate the value of pi, and that's what we were doing up here. So this is sort of the mathematical, slightly more rigorous way of looking at it. One of the things that's really useful, Monte Carlo integration is really useful for, is for measuring values of unbound samples. So unbound functions, things like the exponential distribution, stuff like that. But we can also do it for functions that are just arbitrarily complex. We don't have to calculate an integral. We can calculate moments, for example, of the distribution function that we're interested in. So let's say we wanted to ask the question, what was the mean and standard deviation of this wild piecewise function? Right? How do we calculate that? And it's actually really easy to calculate, because all we do is we generate our random samples, and then we end up with a distribution that is this red function here, right? So these are our random samples that we can see on the PDF of our random samples, and then we use these distributions, these values, to calculate an expectation, right? To calculate the mean of the underlying distribution. And the mean of that distribution is shown by the black dashed line. So that's the sample expectation that I've calculated from the sampled PDF, the sampled distribution, or rather the samples themselves. And the true mean of that distribution is shown as the orange dashed line. So you can see that this is a very, very good estimate of the underlying expectation of this distribution. And so without knowing anything about the distribution, the actual underlying mechanism behind how this distribution function is defined, we can create, using Monte Carlo simulation, an estimate of its integral, an estimate of its standard deviation, of its mean, and lots of other statistics. So it's a very, very powerful tool for generating sort of summary statistics of multidimensional complex functions. Okay. That's where we're going to be. That's where we end for this particular lecture. The last thing to say is next week's lecture. So next week, we're going to be doing something a little bit different. Next week, I'm actually going to be traveling. I'm going to be on the road. And while I expect to have a stable internet connection. It's not guaranteed. So what I'm going to be doing is instead hosting that lecture is going to be held in what we call the inverted classroom philosophy, something which you're probably familiar with from your other lectures. And what that means is that I'm going to be pre-recording next week's lecture. And so I'll make that lecture available to you on the Moodle page, over the weekend. And then before this time slot next week, you need to go through and watch that lecture. Okay. Now, in all likelihood, I'll split that lecture into little bite-sized chunks rather than having, 1.5 hour video for you to watch, so that you can go through. And then when at our normal meeting time, we're going to have a roughly 1 hour, but, we can speak for an hour and a half or even longer if you want, discussion session about the topic covered in that lecture. I think that this is, while this inverted classroom lecture for next week is birthed from necessity, I think that it actually will be beneficial for us because next week's lecture, to me, is really one of the most interesting in the course. It's all about Bayesian statistics. It's going to be the first lecture in our third section from this course, which is all about Bayesian statistics. And we're going to be going through the fundamentals of Bayesian stats. We're going to be talking about how it differs from the statistics that we've been looking at previously, and some, important things. And some of that is going to be complex. Some of that's going to be complicated. And I think it's going to be really nice for you guys to be able to pause and rewind and say, what was that guy Angus talking about, et cetera, et cetera. And then we will meet next Wednesday together at our normal time slot. And instead of having this lecture, we'll have a discussion session for as long as you guys want. Okay? Hopefully that's clear for everyone. If there's any questions, as always, feel free to post them on the Slido. It'll remain open. And if you would like to stick around after everyone shoots off and ask me questions directly, then of course you're more than welcome. But other than that, that's it for today's lecture. Thank you all for coming, and we will see one another at the discussion session next week.